Humanity has been using renewable energy sources for its own benefit since the dawn of history, probably without thinking much about their nature. On the other hand, the use of non-renewable natural resources is a relatively new thing. When Marco Polo traveled to China in the late 13th century, he described the burning of a substance then unknown to Europe, namely coal. Its use did not become widespread in Europe until the Industrial Revolution in England in the 18th century. The drilling and use of oil began around the 1850s, and the natural gas that appeared in connection with it was initially seen only as a byproduct to be burned, until its use became widespread in the early 20th century. The peaceful use of nuclear energy in energy production began in the 1950s. Renewable energy production is a key part of the global transition toward cleaner and more sustainable power systems. Unlike fossil fuels, renewable energy sources come from natural processes that are continuously replenished, such as sunlight, wind, moving water, and organic materials. These energy sources help reduce greenhouse gas emissions, lower our dependence on non-renewable resources, and support long-term environmental goals. Technologies like solar panels, wind turbines, hydroelectric power stations, and bioenergy systems are making it possible to produce electricity and fuel in ways that are both efficient and eco-friendly. Understanding how renewable energy is produced and how it fits into energy systems is essential for building a more sustainable future. Biomass is one of the most versatile renewable energy sources, consisting of organic materials such as wood and its logging residues, straw, grasses, and oilseeds. These resources can be used directly or processed into fuels for electricity, heat, or transportation. Traditionally, biomass has been combusted to produce thermal energy, especially in district heating systems and industrial boilers. In recent years, however, there has been a significant increase in the use of biomass, municipal solid waste, and animal manure for biogas production through anaerobic digestion. This process yields methane-rich biogas, which can be used for heat and power, or upgraded to biomethane for injection into gas grids. Peat is sometimes classified as a renewable resource, but its regeneration rate is extremely slow, approximately 1 mm per year. It takes around 1,000 years for a peat bog to regenerate into a condition suitable for energy use, making it a controversial and limited option under most sustainability criteria. Biomass plays a critical role in the renewable energy mix, particularly in regions with strong forestry and agricultural sectors, offering both energy security and opportunities for waste valorization. Hydropower is also a renewable resource with a surprisingly complex energy cycle. The sun's energy evaporates water from the ground and water bodies into the atmosphere, where it is transported long distances by the wind to condense back into water and fall to the ground. Water that falls on high plateaus or mountain slopes has a high level of potential energy, which can be utilized by damming the water and directing it to a power plant turbine that turns an electric generator. Less common methods of generating electricity using hydroelectric power include tidal power and wave power. Geothermal energy refers to the solar thermal energy stored in the ground, or water bodies. To recover it, a collection pipe system is installed in the ground or water bodies, in which a heat-recovering fluid circulates. The pipe system can be installed in a vertically drilled well, or horizontally in the ground below the frost line, or at the bottom of a water body, such as the sea or lake. The recovered thermal energy has a low temperature, and its utilization requires raising the temperature using a compressor. The operating principle is the same as in a refrigerator. Solar energy can be harnessed in two primary forms: thermal energy and electricity. One of the simplest methods is through solar thermal collectors, commonly installed on rooftops. These systems use blackened pipes or panels in which a heat transfer fluid circulates. The dark surface absorbs solar radiation efficiently, heating the fluid, which can then be used directly for domestic hot water or for space heating in buildings. These systems are cost-effective and widely used in residential and small-scale industrial heating. Electricity from the sun is generated using photovoltaic PV panels, which differ fundamentally from traditional power generation. Unlike conventional power plants that rely on rotating generators, PV panels generate electricity through semiconductor technology. When sunlight strikes the surface of the panel, it excites electrons in the semiconductor material, typically silicon, creating direct current (DC) electricity. This is then converted to alternating current (AC) using an inverter, making it usable in households and the electrical grid. Recent years have seen notable improvements in efficiency, with modern panels commonly reaching over 20% conversion efficiency. At the same time, manufacturing costs have decreased significantly, making solar energy more accessible and widely adopted in both residential and utility-scale applications. However, a key characteristic of solar power is its intermittent nature. The amount of electricity produced by PV panels depends on the intensity and duration of sunlight, which can vary throughout the day and across seasons. Production drops significantly during cloudy weather and ceases entirely at night. This variability makes solar energy non-dispatchable, meaning it cannot be produced on demand without the support of energy storage systems or grid balancing solutions. Despite this, solar energy remains a vital component of the renewable energy mix, offering a clean, silent, and modular source of power with minimal environmental impact during operation. Wind power has been utilized for centuries, originally through mechanical windmills used for tasks such as grinding grain and pumping water. In modern applications, small-scale wind turbines have been employed for decades to generate electricity in off-grid settings, typically for battery charging in remote or rural areas. In recent decades, the focus has shifted toward large-scale grid-connected wind turbines for commercial electricity generation. Around the early 2000s, the rated capacity of typical wind turbines was approximately 1 megawatt (MW). Today, onshore turbines commonly range from 2 to 6 megawatts, while offshore turbines can exceed 10 megawatts, with prototypes reaching even higher capacities. This significant increase in unit size has directly contributed to a reduction in the levelized cost of energy, LCOE, from wind power. Technological advancements such as taller towers, longer rotor blades, and more efficient power electronics have allowed turbines to access higher altitude winds, which are generally stronger and more stable than those closer to the ground. Modern wind turbines rely on sophisticated control systems to optimize energy capture and ensure operational safety. These systems continuously monitor variables such as wind speed, wind direction, rotor speed, power output, and mechanical stress. Two key control mechanisms are pitch control, which adjusts the angle of the blades to regulate the rotor speed and maintain optimal aerodynamic efficiency across varying wind speeds. Yaw control, which rotates the nacelle, the housing for the generator and gearbox, so the rotor always faces into the wind. In high wind conditions, the control system can partially feather the blades, or apply braking to limit power output and prevent structural overload. In low wind conditions, the system maximizes blade exposure to capture as much energy as possible. These adjustments are made in real time through sensors and automated algorithms that balance performance, efficiency, and durability. As land-based deployment becomes more spatially constrained, due to environmental, logistical, and land use considerations, interest in offshore wind energy has grown rapidly. Offshore environments offer higher wind speeds, fewer space limitations, and the potential for larger-scale installations. In addition to fixed-bottom offshore turbines installed in relatively shallow waters, the development of floating wind turbine technology now allows wind energy harvesting in deep-sea locations, greatly expanding the usable area for wind power generation. Thanks to these technological advancements, wind energy has become a critical component of modern renewable energy systems, contributing to both grid stability and large-scale decarbonization efforts. One of the main challenges of integrating wind and solar energy into modern power systems is their intermittent nature. Unlike conventional power plants that produce electricity continuously and on demand, wind and solar output fluctuates depending on weather conditions, time of day, and season. To ensure a reliable and stable electricity supply, various strategies are used to manage this variability. These include 1. Energy storage systems. Batteries, particularly lithium-ion batteries, are increasingly used to store excess energy when production exceeds demand, for example during sunny or windy periods. This stored energy can then be released when production drops, helping to balance short-term fluctuations. Other storage technologies include pumped hydro, compressed air, and emerging options like thermal and hydrogen storage. 2. Flexible power generation. Modern grids still rely on dispatchable power sources, such as hydropower, natural gas, or biomass plants, that can be ramped up or down quickly. These sources act as a backup to maintain supply when renewable output is low. 3. Grid interconnection and smart grids. Wider regional grid interconnection allows electricity to be transferred over long distances, from areas with excess renewable energy to those with deficits. Smart grid technologies use real-time data, sensors, and automated controls to better match energy supply with demand, and to integrate a higher share of renewables without compromising reliability. 4. Demand-side management. Consumers can also play a role in balancing the grid. Demand response programs encourage users to shift their electricity use to times when renewable energy is abundant, for example, by charging electric vehicles during peak solar hours, or reducing industrial load during wind lulls. 5. Forecasting and predictive control. Improved weather forecasting and data analytics enable grid operators to better anticipate renewable energy production. Advanced models predict how much solar or wind energy will be available, and help coordinate other energy sources accordingly. Together, these strategies form a flexible and resilient energy system, capable of integrating high shares of renewable energy. While intermittency presents a technical challenge, it is being addressed with a combination of technology, infrastructure, and system-level planning, paving the way for a cleaner, more sustainable energy future. The role of biofuels in renewable energy production has grown significantly in recent years. This development is driven by both environmental goals, such as reducing greenhouse gas emissions, and by advances in conversion technologies. Modern production methods now make it possible to manufacture biofuels from a wide range of raw materials, including agricultural residues, forestry byproducts, municipal waste, and dedicated energy crops. Biofuels can be used in both transport and power generation, serving as direct replacements or blends with conventional fossil fuels. This makes them especially valuable in sectors where full electrification is challenging, such as aviation, shipping, and heavy-duty road transport. In addition to bio-based fuels, there is increasing interest in electrofuels, or e-fuels, which are produced using electricity from renewable sources. This category includes green hydrogen, as well as synthetic fuels like ammonia and methanol, which can be manufactured using renewable electricity, water, and captured carbon dioxide. These fuels are considered part of the renewable energy mix when their production inputs are sustainable. As the circular economy continues to evolve, even carbon dioxide emissions currently treated as waste may become valuable feedstock. For example, CO captured from industrial processes or power plants can be used to produce synthetic fuels through Power-to-X technologies, closing the carbon loop and contributing to climate-neutral energy systems. Together, biofuels and renewable electricity-based fuels expand the toolkit for decarbonization, offering flexible, scalable options for storing and transporting renewable energy in chemical form.